All right. So today we're going to work through 2.5. You've probably noticed already that we're plowing through Unit 2 wicked fast. All right. We're going to be through the 5th topic already of Unit 2 after today. There's only 7 topics in Unit 2, which probably is a little scary. Topic 6 and topic 7 are going to slow us down drastically. Okay, so we absolutely will not have a test next week. No chance that that is happening next week, but I would anticipate that we do have a test the week after that. Okay, Unit 2 is a small unit. Unit 3 is a behemoth. So we won't test on Unit 3 until we've got half of you guys back, alternating weeks or whatever the heck we have going on. So by the way, if you haven't picked up Unit Pack 3, that's currently on the first floor. So yesterday, today, and tomorrow is another supply pickup. I hope that's been communicated pretty well to you and your families. But please, if you have not snuck into the high school, and I said that at the same thing yesterday, you're not sneaking in. If you haven't, come to the high school and picked up your stuff, please do so, because I've got another unit pack down there for you. And we will get to that prior to us actually being back in person. So you're going to need those note sheets and the homework sheets from that unit. They're all posted, obviously, and if you have printing capabilities, you can do it that way. But it's certainly, I would make the school pay for those printing costs and not your personal printer, because printer ink is ridiculously expensive. All right. Anyway, let's do 2.5. So 2.5 is on Lewis diagrams. And this is a topic that in, I would say probably about 80 to 90% of high school chemistry classes around the country, I bet you this is getting taught to general chemistry kids, not just AP kids. There's no real reason why Shradler and I don't teach this for general chemistry. Just, I don't know, one of those decisions we made to leave it for AP and ignore it in general chem. But this is very much a general chem topic in a lot of high school classrooms. So let me talk about what Lewis diagrams are. So effectively, it's just a representation of a molecule. So we've represented atoms with models as well, right? We had like the Bohr model, B-O-H-R model of an atom. And that's what we had, the nucleus, and then we had like the shells or the rings of the electrons around the outside. That's called a Bohr model. So a Lewis diagram is effectively similar, except it's representing a molecule. It's a diagram to represent how the electrons of a molecule are kind of arranged, okay? So there's a whole bunch of rules. This is what you see at the top of that sheet. Lewis diagram rules, and there's just a wall of words. I'm not going to read through these until we have an example. It's much better to do this in context than it is without context. So I'm going to completely skip these rules until we actually try an example, and then we'll walk through them one by one to make sure that we're doing it appropriately when we have something to actually look at. So let's refresh a couple little topics first, just to make sure, because these are some things that we're going to need in order to be able to draw these Lewis diagrams correctly. So fill in the table with the correct number of valence electrons. Go for it. I don't think you need me. I've got 7 different elements there. If you have a periodic table nearby, please have a periodic table nearby. Write that in. I'll give you a good 30, 40 seconds here to think about it, and we'll go through the answers in just a little bit. All right. For valence electrons, again, these are the outermost electrons, right? These are the electrons that are involved in bonding. If electrons are being gained or lost, it's the valence electrons that are being gained or lost. These are the electrons that are doing the chemistry, okay? We have core electrons, and we defined that earlier in the year. And they're obviously a part of the atom, but they're not the electrons that are involved in bonding when we make covalent bonds, or you know, when we transfer electrons for ions or to make ionic compounds, they're not really involved either. It's always the valence electrons, always. So to determine the total number of valence electrons in an atom, all we really need to do is look at the column. Column 1 has 1, column 2 has 2. If we skip the transition metals, column 3 or 13 with boron at the top has 3, and then 4, 5, 6, 7, 8, so on and so forth. So nitrogen has 5 valence electrons. Chlorine has 7 valence electrons. Carbon, 4. Beryllium, 2. Oxygen, 6. Aluminum, 3. And phosphorus, another 5. Yeah, what is that? What am I doing? Let's try 4. I think I must have been looking at the C or something. That was weird. Anyway, so it's pretty easy. I think you know how to do this. It's just the column number. That's all this really is. How many valence electrons an atom has or an element has is 100% based off of that column number. Now, this really matters with Lewis diagrams, what I'm going to teach you today. You have to be able to correctly identify the valence electrons, because if you can't, we have no chance of getting the Lewis diagram correct. All right, so question 1 underneath this little table, how do you know how many valence electrons an atom has? You can use the column number. Now, what you have to be careful of there is that on some periodic tables, the last 6 columns, you know, the boron, carbon, nitrogen, oxygen, the halogens, and the noble gases, those columns or those families, sometimes they're numbered 13 through 18. In that case, it would be like the ones place of that number, right? So if I'm in column 15, it has 5 valence electrons. Column 17 has 7 valence electrons. It just depends. If you're looking at last year's periodic table, we have Roman numerals above the columns, and they would match 1, 2, 3, 4, 5, 6, 7, 8. If you're still using last year's periodic table, which I do generally recommend. It's a pretty good periodic table. So number 2, if an atom is stable, how many valence electrons would we expect it to have? So when it comes to stability, generally speaking, atoms and ions and molecules are stable when atoms have 8 electrons nearby. Okay. This is proven by looking at the charges of our ions, right? If I make oxide, for example, which is O2 minus, what I'm doing to do that is adding 2 electrons. Well, oxygen would have started with 6 valence electrons, and if I add 2 more, that would get us up to 8. That would be stable. If you look at all the noble gases, the very last column, they all have 8 valence electrons with the exception of helium, which is in row 1. And those are the stable elements, right? We recognize that 18th column or the 8th column, those are all stable atoms and elements. So question 3, how many electrons are in a covalent bond? I've said this a couple times over the last 3 days. Hopefully you've caught it, but if we have one bond, a covalent bond, that's going to contain or be sharing 2 electrons. Okay. Now, Lewis diagrams, which is what we are talking about today, these are for covalent molecules, not ionic. All right. So when I'm talking about Lewis diagrams in the future, please be aware that this is specifically for covalently bonded molecules, not ionic bonds. All right, couple other intro things, and then we'll start trying some examples. Ethynyl methyl ether, which is an organic molecule. I do not get to teach you organic chemistry, or at least I don't get to teach you organic chemistry before the AP test. There is 0 organic chemistry on the AP test, which is really sad because it's my favorite type of chemistry, and I would love to teach organic. I don't know, I thought it was really fun in college, and I did organic chemistry research in college. There's a lot of people that despise organic chemistry with a passion because it's kind of the weeding out course for nurses more than any other major, maybe. If you're a nursing major, every nurse on the face of the planet pretty much despises organic chemistry because that's like the weeding out class or the hurdle class that you need to be able to pass. But don't be scared. Organic chemistry is awesome. It's the best. Okay, I'll teach now. we have this molecule. I have a diagram drawn off to the left for you to kind of look at. There's carbons, there's hydrogens. We have an oxygen in the middle. The name doesn't really matter. I'm just having fun. So when you hear the word octet, what number comes to mind? Of course, the prefix oct is implying 8. Okay. And then the next question I have is, what is the octet rule? We haven't learned this yet, but essentially the octet rule says this. Atoms prefer 8 electrons nearby. Now, I use the word nearby because we can have electrons near atoms in different ways. And I'll talk about that when I look at this molecule in just a second. Okay? So the octet rule is something we're going to use today. I'm going to expand or modify the octet rule tomorrow. No, I suppose next week. I'm sorry, we have a lab tomorrow. Tomorrow's Friday. But I'll expand or build on the octet rule a little bit next week. But for now, for today, generally speaking, this holds true. Atoms, when they're in molecules, prefer 8 electrons in the area or nearby in a molecule. So let's look at this diagram for a second. All right, we've got dashes all over the place, and we've got some dots nearby that oxygen. The dashes are representing a covalent bond. In other words, it's representing 2 electrons being shared between the 2 atoms that dash is written in between, right? So I have a hydrogen right here, I have a carbon right here, and then there's one dash between them. That dash is a covalent bond. It represents 2 electrons shared between the carbon and the hydrogen, okay? The other thing we have are the dots. The dots are maybe even a little more simple. These are called lone pairs, all right? And I'll write that down somewhere. It's called a lone pair of electrons. It's 2. Each dot is 1 electron. So sometimes in our molecules, a lot of times in our molecules, actually, we have extra valence electrons that aren't actually in any bond. They're just kind of hanging out nearby a specific atom. So in this instance, we have 2 lone pairs nearby that oxygen. But each dot is 1 electron. Okay, so when you see a dash, it's 2 electrons. When you see a dot or individual dots, each of those would represent 1 electron. And oftentimes, almost always, they come in pairs, and we call those lone pairs. They're not bonding electrons, they're just electrons that are nearby an atom in a molecule. Okay, so let's look at this. We can analyze how many electrons are nearby these atoms by observing all of the dots and dashes in the vicinity. Now, if I look at this carbon, let's look at this carbon over here, this guy, okay? That carbon right there has 1, 2, 3, 4 dashes coming off of it. In other words, it has 4 covalent bonds attached to that carbon. Each of those covalent bonds holds 2 electrons. So in total, nearby that carbon, it has 2, 4, 6, 8 electrons. This is what the octet rule is. The octet rule says that in order for a molecule to be stable, or atoms within a molecule to be stable, they generally have 8 electrons nearby. This carbon that we just looked at has 4 bonds. Each bond has 2 electrons. It satisfies the octet rule, is the way you could think of that as. Okay? Now, we also have the oxygen in the middle, where I just outlined that lone pair, right? The oxygen in the middle has 2 dashes coming from it. That's 2 bonds. Each bond has 2 electrons, so 2, 4. And then it has 2 lone pairs, 1 above, 1 below. 2, 4 more. In total, it has 8 electrons. It satisfies the octet rule. That's exactly what we want to see. When we make molecules using Lewis diagrams, or when we make molecules in general, again, the rule is that if there's 8 electrons nearby, that represents a stable number of electrons. So the carbon's good, the oxygen's good. What about the other 2 carbons? Well, the other 2 carbons have a double bond between them, which is 4 electrons, right? Each bond is 2 electrons. And if you count up the dashes nearby, each of those carbons also satisfy the octet rule. So in question C, which atoms in the ether, which is the name of the molecule or a part of the name of the molecule, which of the atoms in this molecule follow the octet rule? The carbons and the oxygen, right? All 3 carbons and the oxygen all follow the octet rule. Every single one of those atoms has 8 electrons nearby. Those could be bonds, represented by the dashes. Those could be lone pairs, represented by the little dots, or some combination. Question D, which of the atoms in the ether don't follow the octet rule? And that's all of the hydrogens, right? If you look at all the hydrogens, each hydrogen has 1 bond coming from it and no lone pairs anywhere nearby. The hydrogens all have 2 electrons nearby. But if you stop and think about it for just a second, and if you look at your periodic table, that actually kind of makes sense, because hydrogen's in the first row. It's the very first element. And in order to get to the first noble gas, which is helium, all we need to do is add 1 electron. In other words, 2 electrons is also stable, assuming that you're looking at hydrogen, right? When you have a second electron for hydrogen, it represents a noble gas electron configuration, which is stable. So hydrogen is the one element that will always break the octet rule, or I could say it the other way. It's an element that will never follow the octet rule, but it makes sense why it shouldn't. It's in the first row. It only needs 2 electrons to be stable, not 8 like everything else, right? So the elements that, or the atoms that don't follow this are the hydrogens. All of the hydrogens are only needing 2 electrons nearby, and that's going to be a single bond, and it's good to go. All right. How many bonding pairs of electrons are in the ether? What do they look like? Well, let's count them up. Bonding pairs are the dashes, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I see 10 bonds. What do they look like? They look like this. They're a dash. Okay, up, down, angled, doesn't matter. 1 dash is 1 bond. Doesn't matter the direction that it's going. How many lone pairs of electrons are in the ether? Well, we've got 2 lone pairs, and what do they look like? They're dots. Okay, now that's very simple, but it's important, right? When we're counting electrons and we're doing these Lewis diagrams in just a second, we need to make sure that we're counting correctly. Each dash is 2. Each lone pair, which is 2 dots, is 2. Okay. All right. So I've got 6 examples at the bottom of this page, and then we'll call it a day. We're going to go through and draw some Lewis diagrams for some simple molecules. I've got fluorine gas, oxygen gas, liquid nitrogen, cyanide ion, water, and carbon dioxide. So let me get you started a little bit on a couple of these, and then we'll give you a shot and see how you're picking things up. So now is when I want to look at those rules. Okay. So I'm going to grab my paper copy and go back through them. And you can do the same. They're obviously right above of what we're just up to here. So I don't want to go back on the presentation because then I can't see what I'm doing. All right. So rule number 1, add up the total number of valence electrons in your molecule from each of the individual atoms. Well, first things first, we probably should have a formula, right? Fluorine gas is diatomic. If you remember, and if you do have last year's periodic table, there's 7 elements that are shaded in, and those are diatomic, meaning that when they exist in nature, they must exist with another atom bonded together. So fluorine, pure fluorine, is F2. I'm sorry, I'm going to move that. I apologize. If you wrote that down and you used a pen, I apologize. I'm going to write that over there because I like to use the right side for something else. Okay, so that's our formula. Now, the question is what's the total number of valence electrons that we have to work with if our molecule is 2 fluorines? Well, we go to the periodic table. Fluorine is in the 7th or 17th column. It just depends upon what periodic table you're using. It has 7 valence electrons. So I have 2 fluorines. They each have 7. I have 14 total valence electrons to work with. And I'm going to write that in the top right corner. Okay. 1A, rule 1A from up above. The central atom of the molecule is usually the one with the lowest electronegativity. The first atom in the formula is also usually the central atom, with the exception of hydrogen. Now, central atoms only matter if you have more than 2 atoms in a molecule. So for the first couple of examples here, it's irrelevant. Okay, so I'll skip 1A for now. Rule 2, use electrons to create bonds between atoms. A bond is 2 electrons. Subtract these electrons from your total. So we're going to draw this molecule. I have one F, one fluorine. I have another fluorine. You cannot make a molecule without at least one bond. So we're going to start there. Each bond represents 2 electrons. I'm going to subtract that from my total. I still have 12 valence electrons to work with. Step 2 is all done. Step 3, add the remaining electrons as lone pairs around the outer atoms. Now, when I say outer atoms, that's getting back to that central atom part of 1A. There's no central atom. These are both kind of outer atoms, you could think of it as. But we're going to add these as lone pairs until we satisfy the octet rule. So remember, each of these fluorines wants 8 electrons nearby. I have 12 electrons to work with still, and I'm going to try to add all of these around the fluorines. So I'm going to go 1, 2, 3, 4, 5, 6. If you look at the left fluorine right now, it has 2 electrons in the bond, 4, 6, 8, because of the 3 lone pairs. That satisfies the octet rule. That's stable. That's exactly what we want to see. On the other fluorine, we'll do the exact same thing. We'll add the other 6 electrons over there as 3 lone pairs. I've added 2, 4, 6, 8, 10, 12 electrons, and I have none left to work with. That's good. That's what we want. The goal is to write these bonds in, add the electrons as lone pairs where needed, and satisfy the octet rule for every atom in these diagrams. Now, step 5 says, step 4 says any extra electrons get added as lone pairs on the central atom. That's irrelevant for this one. And step 5 says, turn lone pairs of electrons into bonds between your atoms if you need more electrons to satisfy the octet rule. Well, we're good. We don't have to do that here because they both have 8. They both satisfy the octet rule. So we're actually done. That's it. Fluorine is all done. That's how the Lewis diagram of fluorine looks. All right, oxygen. Oxygen is also diatomic. The formula of oxygen is O2. How many total valence electrons do we have to work with? All right, we look it up on the periodic table. Oxygen is in column 6 or 16. I have 2 oxygens, each of them with 6 valence electrons. So my total valence electrons is 12 in my molecule. Okay, that is step 1. Again, there's no central atom, no outer atoms. There's only just 2 atoms, so all we can do is make a line. We don't have to worry about step 1A. Step 2, we need to make a bond. So there's my 2 oxygens. I make 1 bond because you can't have a molecule unless there's a bond. That's going to require 2 electrons. I have 10 left to work with. Now, your instinct might tell you, well, there's 10 left. Let me put 5 on one and 5 on the other. That's not going to work. Electrons generally travel in pairs, okay, which is going to lead to an unequal distribution here. We have 10 electrons still to add to our Lewis diagram, and I can't split them up. They have to travel in pairs. So we'll just start adding them. This is step number 3. We're just going to add them to the outside of our 2 atoms here. So I have 2, 4, 6. And then I've got 4 left of my 10 total. So I'm going to go like that and use them all up. Now, if we check for the octet rule really quickly, on the left-hand side, the left oxygen has 2, 4, 6, 8. It's good. It's happy. It has its 8. The octet rule is satisfied. If we look at the other one, it has 2, 4, 6. That's not good. The octet rule is not satisfied for that second oxygen. We have to go a little bit further. So we'll skip step 4, because that's talking about the central atom and outer atoms again. Again, this is an example where there's no central atom or outer atoms. It's just 2, so it's kind of irrelevant. But step 5 says, turn lone pairs of electrons into bonds, meaning like a double bond or a triple bond, if necessary, between your atoms if you need more electrons to satisfy the octet rule. Okay, so let's try that. The left-hand one has 8, the right-hand one has 6. We need more electrons to count for the right oxygen, or the oxygen on the right of my molecule. What I'm going to do is I'm going to take this lone pair right there, and I'm going to change that into another bond. Okay. When I do that, let's check the octet rule again. I've taken a lone pair off the left oxygen. I've made a second bond. Now, they both have 8 electrons nearby. They both are satisfying the octet rule, which is which is stable for atoms and molecules. 2 lone pairs, 2, 4, 2 bonds, 6, 8. Okay, this is the correct structure of oxygen gas. Oxygen gas, O2, has a double bond between those oxygens so that both of those oxygens can satisfy the octet rule. All right, I'm going to give you a shot at liquid nitrogen. The formula for liquid nitrogen is the exact same as it is for nitrogen gas. It's N2, it's another diatomic. I'm going to switch colors. Okay. See if you can go through the steps. Give it a shot. I'll give you a minute and a half here to get ahead of me. How many valence electrons are there total in that molecule? Make a bond between the 2 nitrogens. Add the remainder as pairs of lone electrons around the outside. And then fix the octet rule if you need to in order to satisfy, sorry, make more bonds if you need to satisfy the octet rule. And by the way, if you're feeling like that sort of clicked and that sort of made sense, try cyanide. You can go to the next one. Cyanide is a polyatomic ion, by the way. It is Cn, 1-. So 1 carbon, 1 nitrogen with a 1- charge. It's on your last year's periodic table. But if you're good on liquid nitrogen, try cyanide. And heck, if you're feeling extra fancy, go ahead and try water and carbon dioxide. I'll get to those in just a little bit. But. All right, nitrogen is in the 5th or 15th column. It has 5 valence electrons. I have 2 nitrogens to work with. So the total valence electrons in my molecule are 10. I need at least 1 bond between them to start with. Otherwise, it's not a molecule. And that's going to require 2 electrons. Each bond is 2 electrons. I have 8 left to go. I can equally distribute these if I'd like to. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. That's using all of them. All right. I take a step back. I analyze what I have, and currently neither of them are satisfying the octet rule. I have 6 on the left, 6 on the right. All right, so we need to go further. We need more. So I'm going to start making extra bonds. I'm going to take one lone pair over here, and I'll add it to the middle. Okay? Now how am I doing? Well, the left-hand one has 6 still, but now the right-hand nitrogen has 8. By making a double bond, I've satisfied the octet rule of one of my 2 nitrogens. But I need to go further still, because the left-hand nitrogen currently only has 6 electrons nearby, so let me go further. I'm going to take another lone pair from the other side and make a triple bond. Now, this is the correct structure. Both nitrogens have 3 bonds, which is 6 total electrons, and 1 lone pair, which is 8. They satisfy the octet rule. Nitrogen gas has a triple bond between the 2 nitrogens. Nitrogen gas is it's a very, very, very stable structure. It takes a lot of energy to break down nitrogen gas into other molecules or other compounds, okay? Our atmosphere is made up of 78% nitrogen gas. It's pretty much non-reactive. It's a very, very stable structure, and the triple bond is partially the reason why it's so stable. All right, the next one, if you're ahead of me, go for it. Just keep working. If you're not ahead of me, I'm gonna slowly but surely kind of plow through these, okay? So cyanide, the formula for cyanide is CN 1 minus. I'm gonna put that in brackets because it is a charged polyatomic ion, okay? So CN in brackets with a 1 minus charge on the outside to represent the fact that this is a charged polyatomic ion. Total electrons that I have to work with. Carbon, column 4 or 14, so it has 4 valence electrons. Nitrogen, column 5 or 15, so it has 5 valence electrons. That's 9. But what does that 1 minus mean? It means there's an extra electron. So I have 4 valence electrons from the carbon, 5 valence electrons from the nitrogen, and an extra because of the 1 minus charge. I have 10 electrons to work with. I need to have at least 1 bond between them. I'll start there. I've got 8 left to go. And I could go like that. But if you're paying attention, I have a hunch you've already caught on to what needs to be done, right? This was the same total electrons that we had with the nitrogen example just 2 seconds ago. We're going to end up with the exact same structure. If I take one of these lone pairs and make a double bond, oops, there we go. If I take one of those lone pairs and make a double bond, the octet rule is satisfied for one of the atoms, but not the other. And if I take a second lone pair on the opposite side and make a triple bond, now I've got the correct structure. The octet rule is satisfied for both of my atoms. That's what we want to see. I need to put this in brackets with a 1 minus charge because it is a charged polyatomic ion. I have to represent that there's an extra electron there somehow, some way. So we bracket out that whole structure and put a 1 negative on the outside as a part of, to finish up the Lewis diagram. Water. All right, now we're on to our first example of something with more than 2 atoms. We have 3 atoms in a molecule of water. We have H2O. Total valence electrons to work with. Each hydrogen has 1. Oxygen has 6. Again, that's coming from your periodic table, right? It's the column number. So I have 8 electrons to work with. Hey, we've got the question of a center atom now. That's exciting. We can look at 1A finally. 1A says the central atom of the molecule is usually the one with the lowest electronegativity. Now, we talked about electronegativity on Monday-ish, Thursday-ish. Phone, Chloe, Bro, FONClBr, the 5 most electronegative elements on the periodic table. Oxygen is a part of that group. Oxygen has a higher electronegativity. So based on that first sentence, we should put hydrogen in the middle. But the exception, if you read the whole way through of 1A, says hydrogen is not going in the middle, ever. So by default, it has to be oxygen in the center. I put an oxygen there. I need to make 2 bonds because I have 2 hydrogens branching off of the center. Since I've made 2 bonds, that required 4 electrons. Got 4 electrons to work with. Let's go to step 3. Step 3 says, add remaining electrons as lone pairs around the outer atoms. So our outer atoms here are hydrogens. But if you look at the parentheses of step 3, it says, except hydrogen. Hydrogen only ever wants 2 electrons. If you have 1 bond to a hydrogen, that's all the electrons it's ever going to get. So the hydrogens are ignored once more. Step 4 says, any extra electrons get added as lone pairs to the central atom. That's where they're going to go. Okay. All right. Carbon dioxide. Or sorry, I'm sorry. Let's check our water, right? Water's good. Hydrogen has 2. The other hydrogen has 2. The oxygen in the middle has 8. 2 bonds for 4. 2 lone pairs for 4 more. 8. Satisfied. Carbon dioxide is CO2. Now we can use 1A. The central atom is usually the one with the lower electronegativity. Carbon has a lower electronegativity than oxygen. We're going to put carbon in the middle. Okay. I'm sorry, we should totally get our valence electron count. I skipped 1. Total valence electrons. Carbon has 4. Each oxygen has 6. 6 plus 6 is 12, plus 4 more is 16. Carbon's going to go in the middle because it has a lower electronegativity. Again, oxygen is part of the 5 most electronegative, FONClBr. So we're going to put carbon in the middle. We need at least 1 bond to either oxygen. That requires 4 electrons. We've got 12 left to go. Rule 3. Add the remaining electrons as lone pairs around the outer atoms. Our outer atoms are no longer hydrogen, so we're going to follow this rule. I've got 12. I can add 6 on that one and 6 on that one. And that takes up all of the electrons I have to work with. Now, with the way it's drawn, is the octet rule satisfied for all 3 atoms? It's not. The oxygens are good. 3 lone pairs is 6. Another bond is 8. But the carbon is not good. Carbon currently only has 4 electrons. It also needs to satisfy the octet rule. So we've got to start shifting some lone pairs around. If I take 1 lone pair and make a double bond, that oxygen has 8. 2 lone pairs, 2 bonds. Octet rule is good. The carbon has now up to 6, getting closer, still not quite there. And the other oxygen has 8. It's good. We need to finish the other side. I'm going to take another lone pair, and I'm going to make another double bond on the other side of that molecule. And now, if you analyze the octet rule, every atom is good. 2 lone pairs and 2 bonds for the oxygens, 4 bonds for the carbon. Every single atom has the octet rule taken care of. All right, that went on way longer than I wanted it to. I think I went slow, but that's not bad, I hope. Hopefully what I said made sense to you guys. That's all I have. Topic 1 is due tonight by midnight. Topic 1 is totally on 2.1 and 2.2. Just as a reminder of that, I think I had said that earlier this week as well. If you need any help with that, you can try to shoot me an email or hang out after class right now if you know you have a question offhand. Other than that, we'll catch you guys tomorrow. Lab day tomorrow. You do have a lab assignment to take care of. Have a good one. Thanks for stopping by. See you later. Enjoy the weather tomorrow. It's supposed to be beautiful.
I have a question about the lone pair.